Hello. So here we have a magnetic field, B, of some known value, to the right of this barrier. The barrier's got a little hole in it because it's designed to fire particles through. Alright, I'm firing through this unknown particle. Okay, I don't know anything about it except I know its velocity. Okay, we've given it a velocity, and we know it's a charged particle, and it has some mass or other. We don't know those things. We've given it a velocity and threw it into this magnetic field. Okay, so what happens is the particle's too small and too fast to actually watch these things happen. But after the fact, we see a little impact spot right about here. So somehow this particle hit right there. Using this information and having measured this distance, let's call that D, we are going to find the charge to mass ratio of this particle. Alright, we don't have quite enough information to find the charge or to find the mass, but we can find the charge to mass ratio, Q over M. Okay, so we know the velocity, we know the distance from where it enters the field to where it hits the wall, and we know the magnetic field strength. Alright, so let's think about why this actually happens. Why does this particle turn around and impact the barrier right there? Let's grab another color here. So what's going to happen is, as it enters the magnetic field, there's going to be a magnetic force on it. And in the end, it makes a circle, bink, and hits the wall right there. That's supposed to be a half of a circle. Okay, deal with it. So why that is that you've got your particle, say at this moment after it enters, there's going to be a magnetic force on it, apparently in this direction. Okay, now you could figure out that right from the right-hand rule, and we could also figure out the charge of this particle, which would be, sort of on our way to the answer. The velocity is pointing to the right. The magnetic field is pointing into the screen. So if this was a positive particle, the force would be up in this red spot. So it must actually be a negative particle. Okay, because the force is doing the opposite of what the right-hand rule says. So that means that this is a negative particle. Right there. Okay, so the downward force is going to cause it to turn, right? You've got something that's trying to go to the right with a velocity, but you add this force straight down on it, so it's going to push it downward slightly. So it'll end up moving, end up doing something like that, moving in this direction. So we've got a change in our velocity vector here because it was forced downward. However, the right-hand rule still says that the force has to point toward, well, basically toward the center of the circle. The velocity is in a different direction now, but it's still 90 degrees to the magnetic field. And if you use the right-hand rule, you'll figure out that the force has to point in this direction. And so on. You can keep doing this, and in the end you see that the force is always pointing toward the center of the circle, like that. And it causes it to turn around in a circular shape. Okay, so that's why it'll hit the wall right there. Neat. Now, let's see how we're actually going to do this problem. Well, it kind of takes a little bit of insight to start this one. Again, we know velocity, distance, and magnetic field. Don't want to get confused on that. Okay, so there are forces involved. Let's do a free body diagram. Take a free body diagram of it somewhere along its journey there. I'll just do the picture right at the top where it's entered the field. And, well, there's only one force on it. The forces that I just drew a bunch of, which are magnetic forces, right? The force from the magnetic field. That's the only force on it, so it's not a very exciting free body diagram. However, there is circular motion involved here. So if you've watched my videos on circular motion, or if you remember circular motion, there are some special things that happen. One trick I like to do is, well, when I put my free body diagram axes on, which I should always do, I like to call that the C direction. You can call the other one X or Y or whatever, I don't care. C as in toward the center of the circle, right? That's where this force is pointing, and that's where the force always points, toward the center of the circle. So after you do a free body diagram, you always do Newton's second law. The sum of the forces in the c direction equals mass times acceleration in the c direction, and that is not 0. If you are going in a circle, you have to have some so-called centripetal force, some force toward the center of the circle. You may know it as radial force. So we list out what it is here. So there's only that one force pointing in the c direction. It's that. And recall that you can write the sum of the acceleration toward the center of the circle as v squared over r. Centripetal acceleration is v squared over r, where r is the radius of the circle. That's equal to the magnetic force. Magnetic force, well, we have a few expressions for that. Since this is some particle with some velocity moving through a magnetic field, we'll take this definition. Charge times velocity times magnetic field times the sine of the angle between the velocity and the magnetic field. Okay, let's see, we've got a velocity on both sides. We can get rid of one of those there. Let's start to interpret this a little bit. We don't know, we're looking for m over q, or q over m, I guess we could do either. We're looking for q over m, so we can rearrange for that, but we don't know this r exactly, maybe, or this theta. We have to talk about them in any event. So from my half circle picture, it's clear actually what the radius of the circle is. It's half of this distance d that we know. Okay, so that's not so bad. So r is equal to d over 2. Oops. And as for the theta, well, that's the angle between the magnetic field and the velocity. The velocity is in the plane of the screen. The magnetic field is straight into the screen. So their angle's always 90 degrees. It's always 90 degrees between them. And the sine of 90 is 1. Okay, so we've got m v over, okay, so v over d over 2 is equal to q times b. Alright, this can be rewritten as 2v over d. And we just need to rearrange to get charge over mass. So I'll divide mass over that way, b over that way, and we get this. So the charge per mass ratio of this unknown particle is 2 times its velocity divided by that distance times the magnetic field. And if we had the numbers, we could plug in and find the charge to mass ratio, and then we could look at a big table maybe and figure out if this was like an electron or a proton. Well, we know it's negative, right? So it's not a proton. So that narrows it down right there. But that is the answer. And this concept is used, in fact, to determine the mass to charge ratio of certain particles. I think it's used in some types of mass spectrometers. Okay, thanks.